Hello everyone, I'm glad to share our work, Multi-Temporal Ultra-Dense Memory Network for Video Super Resolution. And this is the outline of this presentation. Basically, video super resolution aims to reconstruct the high-resolution video frames from the corresponding low-resolution video frames. Typically, there are two application scenarios for video super resolution. First, for real low-resolution videos, it can recover the missing details like small objects in the surveillance. Second, for systems with HD imaging capability like satellite, it can alleviate the burden of transmission and storage by compressing the downsampled videos, and then upscale the downsampled videos when needed. Specifically, we have applied our VSR technique to several urgent projects. For instance, we cooperated with Zhuhai Hengqin Company to build a custom surveillance system and adopted VSR to improve the clarity of long-distance marine ships. Besides, in the Meetup video conference system with Suri Company, our VSR is used to save transmission bandwidth during COVID-19 period. And a lot of works have been proposed for VSR. VSR-NET and VESPCN merges frames in the beginning and build a network to extract the features. However, their networks are too shallow and cannot extract deep features. DRVSR adopts the convolutional LSTM layer to fuse the temporal information. Nevertheless, a single memory layer does not have a robust memory ability. Although FRVSR builds a deep network, it is based on single-channel design and is still limited in performance. In video super resolution, there are two kinds of key information, the intra-frame spatial correlations and inter-frame temporal correlations. As you can see in the left image, these similar goals contain a kind of spatially related supplementary information to each other. The right image shows a person's trajectory, which should be seen as motions among consecutive frames, and correspondingly there exists a kind of temporally related supplementary information among video frames. How to reserve and transfer long-term temporal information is also important. Normally, to better capture the above information, we should build a deep network. However, we have found that a network can be too deep to be trained well. To handle the above issues, in this work, we first establish a multi-temporal ultra-dense memory video super-resolution network with a shallow dips but broad widths. Second, we propose an ultra-dense memory block to retain temporal correlations and extract hierarchical information from multiple channels. Third, we present a multi-temporal information fusion strategy to make full use of historical information. It is a great honor that our work has become ESI hot paper and gained peers' positive comments. Here we show the whole architecture of our method. As you can see, our model consists of two subnetworks, the optical flow network and the image reconstruction network. First, we adopt a motion estimation module to predict the optical flow between the current frame and the reference frame. Then we apply a motion composition module to align the current frame to the reference frame. In all, the optical flow network tries to capture the motion information among frames. After that, we build the image reconstruction network to extract and fuse the spatial temporal correlated features. In the end, we upscale the feature and add it to the bicubically upsampled low-resolution input to obtain the final super-resolved result. In the image reconstruction network, we mainly propose the ultra-dense blocks and multi-temporal information fusion strategy. Specifically, we first set ultra-dense residual blocks to extract the spatial features. Then, we adopt ultra-dense memory blocks to fuse, update, and restore features of the current frame. We set ultra-dense residual blocks again to enhance the feature extraction and fusion. As for the multi-temporal information fusion, it reserves the outputs from all previous frames and merges them together. By this way, it transfers the long-term temporal information more directly. This figure shows the structure of UDMB. We first adopt multiple channels of convolutions to extract hierarchical feature maps from the input separately. Then, we set convolutional LSTM module in these channels to extract rather self-independent features and reserve memories. Later, features across all channels and inside each channel are concatenated and convoluted to further enhance the extraction and fusion. At last, features from all channels are merged into one single channel, convoluted and added by the input through the idea of residual learning. As one frame goes through the UDMB, the convolutional LSTM is supposed to merge its feature with the reserved feature from last moment. This way, convolutional LSTM learns to forget the temporal irrelevant information and remember the temporal related information. In all, features are extracted within and across channels in UDMB, through which we build a shallower but wider network. It is worth mentioning that by replacing the convolutional LSTM with normal convolution, UDMB turns into UDRB. We explore the influence of channel number in UDRB. With only one single channel, R100C1 becomes hard to train and behaves even worse than R60C1. With three channels instead, R18C3 behaves a little worse but faster than R60C1, and we choose the channel number as 3 for good balance. Then we verify the memory ability of UDMB. By adding a few UDMBs to R18C3, UDM R6M3C3 behaves a little better but much faster than R60C1. This phenomenon indicates the superiority of the multi-channel design of ultra-dense blocks. In a previous work MMCNN, the model deteriorates when the frame number increases from 5 to 7. In this work, with the help of ultra-dense blocks, our model becomes better with more input frames. Moreover, by adopting multi-temporal information fusion, MT-UDM-F5 outperforms UDM-F5 about 0.09 dB and behaves close to UDM-F7 but runs a lot faster, which proves the multi-temporal information fusion can help to capture the long-term temporal correlations. This is the results on VID4 dataset, and our model surpasses DRVSR 1.3 dB at most. And this is the results on UDM10 dataset. Our model surpasses FRVSR about 1 dB in average. Although our methods need more time for testing, they behave much better and need less time for training compared to DRVSR and FRVSR. As you can see, our model recovers stripes with clear details. We also test our model on real-world IR videos. As seen, it gives a much better result. In conclusion, our model outperforms the second-best method FRVSR about 0.6 to 1.3 dB in average on extensive public benchmark datasets. In the future, we will try to extract and fuse the special temporal correlations directly without the memory module. Thanks for listening, and please refer to our paper for more details.